So let me start, and this is no mere courtesy, by saying what's immense to the organizers and the faraway organizers and the local organizers in particular, to Mirela and Kalin. It's a great pleasure, personal one too, and it's an honor to be invited to this school. I'm grateful for that. It's my second or even third visit to Bucharest, and it's always a pleasure to see how the city is changing for the better. So it's great to be here. And otherwise, I hope to be of service for those of you who learn some higher geometry, which is precisely the subject of my talk. So the subject of my talk is, as you can see, gauge symmetries and their higher analogues. I'm supposed to introduce you quickly as it is, so run you through some higher gauge theory and higher geometry. But in order to say what higher means, we have to establish some reference frame, which will be that lower gauge theory and lower geometry, relative to which I will get high, so to speak, as we proceed. So I wish you a nice getting high with me. All right? So many people use the term rather liberally, the term gauge theory, and it's good to fix a set of elementary notions so that we don't get lost. And I propose to found the discussion on three pillars. So gauge theory to me will be a set of relations, structured relations between them, and a set of propositions relating three sets of physical objects, namely charges and charge currents, that for one thing. Then certain messenger fields. In the old literature they were called intermediate gauge bosons or something like that. And then the somewhat more abstract notion of symmetries, or local symmetries for that matter, of some dynamics, which I will always assume to be described in terms of Lagrangian density, or a thing that generalizes a Lagrangian density in the presence of non-tensorial couplings. So some sort of holonomy, if you will. Okay? And now this is just a set, and now we'll establish a network of relations between the various elements of this set. So first of all, if you have charge currents, they can serve as sources of gauge fields, of those messenger fields. I've written here for you a somewhat non-orthodox, and I'm sorry about it in an orthodox country, but somewhat unorthodox version of Maxwell equations for the messenger fields, or rather curvatures thereof. But this relation is reciprocal, so also we can think of the messenger fields as giving us a background, which will determine the trajectory, well, the charge current in a given space-time. So we think of there being on the space-time metric a messenger field background, and this messenger field background makes the current deflect from the geodesic trajectory, basically. So then, going further, if we have messenger fields, these are intrinsically cohomological objects, as you will be reminded soon. And so they come with some natural notion of cohomological equivalence, in which there appear as something that quantifies this equivalence, smooth profiles in a group. So this cohomological equivalence, think of the equivalence class of potentials for the Maxwell field. There you get functions with values in U1 as or in R, if you will, as a measure of arbitrariness of the choice of the potential for a solution to this equation where J is 0. Okay? And so there appears a group of smooth, or at least locally smooth profiles in a Lie group. We'll later sort of play with the symmetry model and pass to the groupoids and make general categories, but that'll come later. Then, of course, if you have local symmetry of a dynamics given in terms of a Lagrangian density, you may contemplate a scenario in which you reduce the space of internal degrees of freedom relative to the action of a group of symmetries. This is called also gauging. That's one of the instances of this liberal usage of the word gauge. And then, in order to do the gauging in a dynamical field theory, that is, a field theory whose Lagrangian density actually does depend on derivatives of matter fields phi, you need to introduce messenger fields. All right? And then if you have a local symmetries, then among local symmetries you have the global sector, so constant profiles in the group. You can always arrange that. And then you have Noether's theorem, which associates with those global symmetries, if they're continuous, charges, which you may then consider as dynamical objects and make them propagate. And reciprocally, if you have charge currents, they will generate on the level, well, be it on the classical level via the Poisson algebra, or on the quantum level by the commutator algebra, they will generate symmetries of a field theory. So you have this whole web of connections, and the simple standard model, there will be another standard model, the standard model that we typically speak of under such circumstances, we haven't do it. But the standard model of this situation is where you model the charge currents by basically volume of an embedded submanifold, whose intersection with an equitemporal slice is usually assumed to be compact. So this is supposed to be the world volume of the charge moving in space-time, and that's actually the first step towards sigma models that I will focus a lot in my talk. And then the standard action function of such a sigma model, the simplest one you can write is, okay, I told you about geodesic motion of neutral particles, that's modeled by this Lagrangian density. But then there is a metric on the manifold in which the charge point-like particle moves. And then if you want to model via the Euler-Lagrange equations of an action functional the Lorentz-type deflection from geodesic flow, then you just add this geometric coupling of the messenger field, of which you think is a background field, to the world volume describing the history of charge affected by the presence of the background field represented by this form here. And then the standard model is where you take this form, you really discuss the propagation of the point-like charge, so you have a one-dimensional manifold in your space-time to which a one-form couples. Okay? And then the one-form is supposed to be like primitive of the Maxwell field, hence you have a certain redundancy in this description. So this one-form is defined up to what we call gauge transformation, which is just an equivalence on the set of admissible potentials of the Maxwell field, and that gauge transformation is described, at least locally, by U1 valued, in the case of the Maxwell theory, U1 valued profile, profile in U1, smooth profile in U1. Okay, so now let me outline where the parameters lie, which we can and will play with, so as to pass from lower geometry, lower gauge geometry, and lower gauge theory to higher gauge theory. So first of all, you may confront the fact that the topology of space-time is probably non-simply connected, it's probably somewhat involved, and hence, instead of speaking of tensors and playing with tensors, such as global primitives of of the Maxwell field, you're bound to look for local primitives of the Maxwell field and geometrize these as higher geometry above the space-time, or I should actually say constructing a space-time as probed by charged particles. So this metric manifold is a space-time as probed by neutral probes, and then this higher geometric object which geometrizes the Maxwell field in the presence of topological singularities on its support, so on space-time, that will be the space-time for charged probes. So then you get notions such as bundles with connective structures associated with the Maxwell field, for example, or if you further play with, because whatever prevents you, right? At least theoretically, or you may come from the string theory department, and then you're paid for actually considering such situations. So whatever prevents you from however little, I mean. But anyway, you may try to play with the topology of the charge distribution. And rather than considering the propagation of point-like charges, start probing the space-time there with charged loops, or charged paths, or charged membranes. And as you introduce the topology of the charge distribution into the game, actually this higher geometry becomes even higher, so to speak, and it geometrizes as so-called gerbs with connected structure. And that I hope to introduce you to later on. Then you may perform, and this is no coincidence. I call it first geometrization, second geometrization, and third geometrization, which you should think of, try to think of, in parallel with first quantization, second quantization, and third quantization, so to speak. So now we may start to think about those charged currents as localized excitations of a field, and then try to couple gauge fields to that charged field. Okay? That's the second quantization. And then, intrinsically, so to speak, we end up with fiber bundles of whose sections are the charged fields, and we have to couple somehow in a meaningful, mathematically meaningful, rigorous manner, the geometrization of gauge fields, of background gauge fields, to those fields, to those bundles of fields. All right? And then the third geometrization is you may actually employ gauge fields to effect a reduction of the space of internal degrees of freedom. Namely, you can pass from the original space of internal degrees of freedom, say R for a scalar field, R2 or C for the complex Higgs field, or some affine or vector space for gluons, or whatnot. You may actually identify some global symmetry on this space and make it local and reduce the space of internal degrees of freedom by passing to the orbit space of the original space of internal degrees of freedom by the action of the group. And for that, you have to perform integration over all isomorphism classes of geometrizations of gauge fields that you introduced in step 1 already, as coupled to the matter bundles introduced in second geometrization. And this affects reduction of the space of internal degrees of freedom effectively through some homotopy arguments. Okay, either independently of all this blah, or in consequence thereof, and it's always good to be consequential, maybe not in life, but in maths at least. So in consequence of that, we always end up with some sort of categorification of symmetries. So I told you that the symmetry model to begin with was a group acting on a space, be it a space of states of the field theory, be it a space of connections. As a result of this blah, we end up with a categorification of the model. So instead of having a group acting on a set, we may have a generically groupoid. I will tell you what it is later on. Or indeed, we may have more general categories that will happen in the context of having topologically non-trivial elementary distributions of charge, like charge loops or charge paths. There we will encounter categorification of symmetries. Okay, so what is the thing that we want to describe in this context where we have a probe? I should first tell you what a probe is. So a probe, owing to this reciprocity of the relations between charges and messenger fields, a probe is always the source for a field. We cannot do away with that. Unless we sort of say that there are inert probes, and maybe they're not the same as the probes which are sources of fields, but let's not go into philosophy here. Let's assume that charges are both. They feel the background field, and a move along trajectories dictated or co-dictated, together with the metric, the gravitational field, trajectories are co-dictated by the background messenger field, and they also produce this field. So whenever I say probe, I mean it is unaffected by its own field. All right? It produces a very small messenger field for which it is a source, and we are not taking it into consideration. We really see it as something whose movement is dictated by the external messenger field. And then we want to consider the following situation. So probably I'm not visible. Waving my hands. I'm visible. Okay, good. So then we want to consider the following situation. So we could always consider a trajectory of a single probe, but then, actually I prefer to say Dirac tells us to compare contributions to quantum mechanical amplitudes coming from coordinate histories, from coordinate trajectories, be it charged trajectories or otherwise. And I therefore propose sort of referring you to the seminal paper by Dirac from either 32 or 37, I now forget, in which he actually discusses the quantum mechanical relevance of the classical Lagrangian as something which first order in H bar gives you a quantum mechanical amplitude. So an answer to the question, to the probabilistic question about having a particle start at a point Q at time t0 and end at a point Q prime at t1, going through whatever it is going through, like background gauge field and the background gravitational field. We will compare coordinate trajectories. And whenever we compare coordinate trajectories, like in this Aharonov-Bohm effect, maybe I should quickly remind you what an Aharonov-Bohm effect is. So we heard this barrier here in which we cut out two slits. We put a cannon here. The cannon shoots like electrons, electrically charged particles. Then behind the barrier, with two slits in it, we put a detector screen. And then just here, we put a tiny whisker going transversely to the plane of the picture. And within this whisker, we localize, like in a Faraday cage, we localize the source of the Maxwell field. So the two form that you know, the electric combination of electric and magnetic field. So your prime school curriculum is telling you if there is no electromagnetic field, it's not my revolution. I mean, if there is no electromagnetic field here where the particle moves, turning it on and off where the particle doesn't see it won't affect its motion. No, this is not true. And indeed, you see that the diffraction image on the detector screen changes as you turn on the electromagnetic field strictly localized within the whisker. This is the so-called Aharonov-Bohm effect, and you like to understand it by considering the the amplitudes after Dirac, the histories contributing to the total quantum mechanical amplitude coming from starting at the same point, ending at the same point, the detection point, but going along here, and that I want to stress, topologically non-equivalent paths. Paths which cannot be continuously deformed into one another. Why? Because in order to model the whole thing, we have to cut out the point here, which is the singularity point for the curvature of the field A. But once we cut it out, what we end up with as a geometry of the laboratory geometry is R2, imagine a very big, very pricey laboratory, so R2 with the point size. So R2 without the point is non-simply connected, and that's all we need to have higher geometry. Okay, so then, but as we compare amplitudes, or rather after Dirac, exponentiated amplitudes for this path and that path, mathematically speaking, technically speaking, don't take it for a closed curve on which a particle moves. Don't make this mistake, but just comparing the two curves, we get, formally speaking, the action functional for the one cycle in the geometry of the laboratory. So, and a non-trivial one. Why non-trivial? Because we cannot contract it to a point, because that point is excised. Okay? Good. So we have to, so mathematically now we abstract from this physical preparation, and what we have to understand is the action functional for a charged point-like particle moving along, in the sense of this Gedanken experiment, moving along a closed but non-contractible path. And then we see that, the path being non-contractible, or the space-time of our experiment being non-contractible, there may be F's Maxwell fields which are non-trivial classes in the realm of cosmology. All right? And then what do we do? Meaning there is no global primitive for F. So F may be 0 everywhere, but it doesn't mean that there will be like A equal to 0 everywhere. And we have to glue contributions from patches in space-time where still F has a primitive. Well, what springs to your mind is the Poincaré lemma. So you have to make those patches contractible. And this is precisely why the whole thing doesn't work. The whole thing doesn't work because it is non-contractible. You have to make the patches contractible. And you can always cover your manifold, your laboratory manifold, with an open cover, which on top of having contractible elements, so opens, has the property that whenever you intersect a finite number of them, the intersection is either empty or it is contractible again. So the proof is due to violent around. It's different techniques, but anyway. So then you look at F, and you realize that on each open, it being contractible, you can find a primitive, and then if you compare two primitives on the intersection of the opens, you take the exterior derivative of this difference, and it vanishes, because each primitive is a primitive of the same two-form, global two-form. So the exterior derivative vanishes, but then the intersection is contractible, which means that there is a global, on this intersection, there is a global primitive for the difference. And then we move to a triple intersection, OI intersected with OJ intersected with OK, and it's okay to look at this rather strange, unless you know Czech homology, weighted sum of the F's, which appear here, which were smooth functions on the overlaps, to find out that D of this trivially vanishes. But if D of that vanishes, and we're on something contractible, and that something is a function, it means that something, this combination, is a constant. And in this way arrive at 3 index constants, okay, in R. We will further later constrain them by quantum mechanical arguments. And of course, you have to take into account, and that will be the basis of our geometrization later on, you have to take account the inherent redundancy of this description. So you can find a primitive, but non-uniquely, not a unique one. You can replace the one that you have found for F by something from the kernel of the operator here, D. But OI is intractable, so that something necessarily has to be exact. So you may replace the original gauge field by a gauge field corrected by an exact, by the exterior derivative of a function. And then this redundancy propagates downwards this ladder of objects where you have a smooth one forms on opens, with which you cover your laboratory space-time, then functions on their double overlaps, and finally constants on their triple overlaps. Okay, so you have this huge, rather nastily looking hierarchy of objects and their equivalences, which can be arranged neatly in terms of Beilinson-Delimi hypercohomology, but it's just a name after all. Well, up to a point. So let me just do it hands-on, in a hands-on manner. Okay, what is it good for? It is good for actually coupling, although in a non-tensorial way, the background messenger field, AI, represented by this whole collection of AIs, to the current world volume. How so? Well, the first thing that springs to your mind, you play safe and you say, okay, there is this part of the Lagrangian density which defines the geodesic evolution, and then I cut my parameter space into segments, ensuring that for a given embedding map X, which sends me into my laboratory, parametrization map, okay? A given segment lies in a particular open on which F trivializes, then I can just pull back to images of the edges of the segmentation, the corresponding primitives. That's how I started, right? I mean, for a global primitive of F, I could just couple A to the image of to the trajectory, to the current trajectory, to the trajectory of the charge in space-time. Alas, this doesn't work because you have to take into account the arbitrary choices that you made in the first place, like the choice of the primitive. I told you that the primitives are only defined up to differentials of functions on the overlaps. And as you play with this object, you realize that you have a dependence of the thus defined action functional on the arbitrary choice of AI, which localizes at the vertices of the segmentation here, 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 here. Okay, that's by the Stokes theorem, basically. Okay, because you have the difference, which is d alpha I living on this. So by Stokes theorem, you put it to the vertices, and so you have to put something at the vertices in order to make the formula independent of the arbitrary choices made. And as it turns out, you have to take a weighted sum. Don't look at this formula too closely. You'll have it at home. You can make it put you to sleep or something like that. You can hug it and draw pictures around it and stuff. But the point is to see the conceptual picture. And the conceptual picture is that at vertices, you have to correct the Ansatz null with contributions from vertices given by the functions f that appeared here. Right? And then the whole formula turns out to now not depend on the choices made, previously depended functionally on the choices made at vertices. Now it depends on the choices made, but through constant c. And if classically, I mean, if you have this naive approach to the Lagrangian density and the action functional as a crank that you turn to produce the Euler-Lagrange equations, then you say, well, I just, if I change my choices, arbitrary choices, I'll end up with an action functional which differs from the original one by a constant. So who cares? Dirac does, and because Dirac does, and we like Dirac. He had three names, one thing, and many other good properties. We look at this as this Dirac-Feynman amplitude, which is the exponentiated classical action functional, and we make sense of Dirac's insistence on this being well defined as the first term in the H-bar expansion of the quantum mechanical amplitude. And we want to make this work, meaning we want to have it well defined, maybe not the action functional, but the quantum mechanical amplitude should not rotate as we change arbitrary choices, such as the choice of a primitive of the Maxwell field, right? Because this amplitude, remember where it came from. It came from comparison of amplitudes on cobordant paths. So it will be the amplitude that affects the diffraction image. So it better not change because the diffraction image is something and not something else if we change the coordinates, so to speak. Okay, but this means, and this is a small computation, that theCijk's which quantify the non-invariance of Ansatz 1 under the arbitrary choices, that they have to lie in 2 pi z, not just generically in R, but in 2 pi z. Good. Yeah. All right. So now we have a well-defined Dirac-Feynman amplitude, which takes a loop in X, a smooth mapping from S1. We're still in this Aharonov bomb. This can be given up at some point, but at a price, which I don't want you to pay yet. I've paid it, but it cannot be on me, alas. So, good. Anyway, so we have this exponentiated metric term, which we perfectly understand. And now we have this strange-looking term, which I gave you before, which has the or is called the line holonomy of a bundle. And here's your first encounter with higher gauge geometry. We get a Maxwell line bundle, or depending on, you can have a frame bundle for that line bundle, so a U1 or CX principal bundle over spacetime X. And this guy is supposed to geometrize the Maxwell field. And it can only be formulated for a Maxwell field whose integrals over, when rescaled by Q, the charge to which it couples, integrals over integrals over closed two-dimensional submanifolds in X lie in 2 pi z. You might think like this pull out of the hat, but actually the fact that this is so is the same as saying thatCijk's lie in 2 pi z, which is an exercise that I give to you. Okay? We can do it in the tutorial to show how this comes down. So now let me, in a very elementary way, do the geometrization. So what do we have at the outset? We have a bunch of locally defined smooth one forms, which glue somehow on overlaps. That gluing satisfies some co-cycle condition of this. So I propose, since I now put f, so everything is up to 2 pi z, because the Dirac-Feynman amplitude doesn't, it's in the kernel of the exponential with an I in front of it, as Dirac told us. So I instead of fighting with the Fij's, I propose to work with the exponentiated Fij's, and then this funny expression, this one, namely this funny weighted sum here, that it gives something in 2 pi z, means that if I consider the exponentiated Fij's, this is the product of the exponentiated Fij's and Oyjk is 1, and this is called the co-cycle condition for Gij, one co-cycle condition. Okay, so I have this co-cycle in U1, and I have this form. So now, with hindsight, I propose that we look at the following manifolds. I take the disjoint union of the trivializing opens, OI, with U1, and on it I put the following one form. So it's the left invariant, well, it's an abelian group, so never mind, the left invariant Maurer-Cartan form on the fiber of this trivial bundle, OI times U1, and AI on OI. And why? Well, the point is that if I identify, so now I look at OIJ, I have two descriptions. One coming from the OI and one coming from OJ over OIJ. So here I have AI, the messenger field AI. Here I have the messenger field AJ, and I have a gluing for them. Well, as it happens, this gluing is such that I can define a globally smooth one form on the quotient of this disjoint union by the equivalence relation defined by the cocycle. So the cocycle being a cocycle in U1, it defines an equivalence relation on this set. It can be equipped with a smooth structure, a quotient smooth structure, and so this is a surjective submersion over X, the original one, with a typical fiber U1, and on it, not quite with free, but from what I said before, I get a globally smooth one form. That's the gluing for the AI on double overlaps. And then I observe further things, which I will subsequently abstract, namely that on this bundle, there is obviously an action of U1. How so? Well, you see the gluing, look at the gluing. The gluing is by the left action of U1. It will become important later on. Here, with U1, we shouldn't put too much weight on it. But if it's not U1, imagine for a moment that it's not U1, the fiber. Then it matters from which side you act. And since Gij, I expressly wrote it as acting from the left, the gluing is from the left, then I still have a right action of the group U1, which survives the gluing. Okay? Which is glued nicely, because the right action, the commutant of the left action. And so we have a right action, which is of course as regular as it gets, because it's modeled on the right multiplication by a group element in the fiber. So it's free, transitive, and whatnot, and proper. And proper, that'll be very important. And with it, we can associate fundamental vector fields of that action. And now, our form happens, as you can readily convince yourself in this simple example, satisfies the following conditions, which will then make part of the definition. Namely, it's right invariant. This will have to be correct, right? But anyway, here it's just right invariant. And it has the nice and strange property that if I evaluate it on the fundamental vector fields of this right action, any such fundamental vector field is a mapping, an equivariant one actually, from the algebra, the Lie algebra of the group acting, into the space of vector fields on which the group acts. All right? And then, so the funny thing is that this one form, when evaluated on any such fundamental vector field, reproduces the element vector in the Lie algebra with which we associated the fundamental vector field. And so, I should still geometrize the equivalences. Remember the AIs? They were sort of an intrinsically cohomological object, and they had those cohomological equivalences. Different choices, quantifying the different choices of the primitive AI, the functions Fij, and so on. So I'd like to model the automorphisms of L, of my thingy L, the surjective submersion with a typical fiber and extra structure, on cohomological equivalences. And then it turns out that the right notion is a morphism of surjective submersions, which sends fibers to fibers and preserves the one forms. So if I have two such surjective submersions, I have a one form here, I have another one form there. I consider morphism of surjective submersions, which covers the identity on the base, doesn't change the base point. And if I pull back this one from here, I reproduce what was previously there, the one form that was there in the first place. So connection preserving automorphisms. Locally modeled on the data hi, which are just exponentiated alpha i's, which appeared in this cohomological ladder. Oh yeah, here you have it, right? So you have that AI is AI plus the alpha I. I mean, you can replace it with AI plus the alpha I, and here are the alpha i's. And you just model the automorphism locally on these. Good. So the first observation is that such automorphisms preserve this object that replaced tensorial action functional, namely the holonomy. And that's good news, right? Because our action functional now formally is invariant under automorphisms of this geometrization of the Maxwell field. And while we're speaking about the holonomy, I feel obliged to mention, which will play a role in the second lecture, something that will play a role in the second lecture, namely that as it happens, if you evaluate this holonomy on, you could actually take it as a co-defining feature. If you evaluate this holonomy on a loop which bounds something, which, so as a Seifert surface, so to speak, a disk there, in unlike our loop in the Aharonov-Bohm setting. If it bounds, it should be the exponential of an integral over that disk bounded by our loop of the two form. Now clearly, so the loop that we considered previously, the difference of the two coordinate trajectories, doesn't bound anything, and luckily so, I mean consistently so, because had it bounded, we would have had zero on the right hand side. There would be no diffraction image change when turning on F within the wisdom, which is excised from this model of our laboratory geometry. Okay, so now an abstraction. Finally an abstraction. So what have we got? We have what is known as a principal bundle with a typical fiber given by a Lie group G. Here's the typical fiber. So it's a fiber bundle, which means it has local trivialization. So its base admits an open cover on elements of which the bundle can be diffeomorphically modeled as the Cartesian product of this element of the open covering times the typical fiber, which is a Lie group. In our case, it was U1. And then it has a right action locally modeled by right translations in the group. Okay? And then we needed to come with a principal connection one form, that is a one form on the total space. In our case, it was this quotient of the disjoint union of the local models by the co-cycle, by the equivalence relation given by the co-cycle. So it's a one form on the total space of the principal bundle with values in the Lie algebra, something which we didn't see previously because the Lie algebra of U1 is R, and so we didn't see it. And then the local presentation should be as we obtained it previously, up to a small subtlety which was invisible due to the triviality of the adjoint action of the group of the abelian group U1 on itself, but that's what it is. And with the defining properties. So not any connection, but one which is equivariant with respect to, so think of this one form as a mapping from the tangent of P to the Lie algebra
So the tangent of P is the G manifold with the action given by the tangent of the action R, and so is the Lie algebra. There you have the adjoint action of the Lie group on its Lie algebra, and A should be equivariant. That's what this argument says. That's what this condition says. And furthermore, it should have the property that we saw before. So if you contract it with the fundamental vector field, and if you take the ensemble of the collective fields, you span the so-called vertical distribution of P, so the tangent of the fiber, if you will, then it should evaluate in this simple fashion, which I discussed previously. Yeah, and then there is an object which you can associate with this connection, which is the so-called its curvature. Well, I don't want to discuss the Abelian part of the curvature, the rest of it. It's not quite an object such as the Maxwell field, which is an observable. It's a tensor under gauge transformations, but sort of let me put it under the carpet. Okay, and then we have automorphisms, which also can be abstracted and geometrized. So these are connection-preserving automorphisms of principal bundles. For them to be automorphisms of principal bundles, they have to be G-equivariant. So G-equivariant fiber bundle morphisms, which preserve connections and are locally, which are locally modeled on left action by smooth profiles in the group. So here we are, smooth profiles in the group. We have jumped from currents to messenger fields to their equivalence classes to groups, and smooth profiles in a group of the space-time, locally smooth profiles. Okay, so the second geometrization now. So the second geometrization, we now want to view the currents as localized excitations of a charged field. Okay, so Nutter's theorem kind of suggests how we should proceed. So we should proceed by first taking a field theory. I will tell you what it means to me, and for the intents purposes of this topic will suffice. And then look at global symmetries and reenact this other notion of gauging, so gauge a global symmetry, that is render it local. And in order to render it local, we'll have to introduce messenger fields into the game, according to one of the arrows that I drew for you. And the way they couple in a geometrically perfectly canonical way, and this will be the coupling between the gauge fields and the matter field charged under those gauge fields. So this is how we establish it. We are actually using those arrows, not just drawing them on the table. All right? So they in a sense, the three pillars offer for us the three directions of attack on the notion of a gauge symmetry. Okay. So what is the field theory for me? Well, it's a distinguished functional, taking values in U1, on the space of sections of a bundle, a fiber bundle with a typical fiber which represents the internal degrees of freedom of your field theory. Could be R, if you consider a temperature field. Could be a vector field. It could be R3 if you consider the velocity field in a river. Could be R4 up to equivalences, affine equivalences, if you're considering a gluon field, and so on and so forth. Could be R2 if you consider a complex fixed field, and so on. So forth. But anyway, there's a fiber bundle here whose sections are fields over my spacetime. Over any point, the section it sits just squarely in the fiber of that point. So it's an assignment of a combination of the internal degrees of freedom to that point in spacetime. So we're not removed somehow from the intuitive notion of a field. Yep, and then we identified global Lie group of symmetries by looking at those. So we want them to be modeled on the action of a Lie group. It's something we come with, or I come with to this discussion. There's a Lie group which knows how to act on the typical fiber, on the space of internal degrees of freedom, if you will. It's locally modeled. Well, yeah. So the local description of the corresponding automorphism of the field bundle is just modeled locally on this action of G on the typical fiber of the bundle. And then the symmetry condition is that the Dirac-Feynman amplitude, now we know that we should stick to the Rafal amplitude and not just to the action functional, should be invariant under this action in an object. So for simplicity, because that will be also sufficient to consider this so-called associated construction, let me assume that the field bundle is trivial, so that fields are just, so being sections of this field bundle are just smooth maps from space-time to F. Okay? This will suffice. And so now our goal is to replace the original bundle, curly F, with another one which models field theory with the same degrees of freedom, so another bundle with the typical fiber straight F, on which, however, we have an action of yet to be determined smooth or locally smooth profiles in the group of symmetry G. So not just G, but smooth profiles over the spacetime in G. Okay, so how do we proceed? The point of departure is what is known as the quotient manifold theorem in differential geometry, which says the following. If you have an action, a smooth action of a Lie group on a manifold, which is free and proper, let me just say that properness is a topological property of the action. Let me not go into there. I'm happy to discuss it in the tutorial session. There is a certain property which can be phrased in terms of convergence of sequences or properness of a certain map associated with lambda. It's a property, okay? Properness is the property, freeness you know. Then there exists a unique smooth structure on the space of orbits of that action, such that, essentially unique, such that the projection which assigns to a point in the manifold acted upon its orbit is a surjective submersion, okay? Why does this matter? Well, first of all, note that an example of such a situation is the right defining action of the structure group on the total space of the principal bundle. This is proper, free, fiber-wise, free, also fiber-wise transitive, and proper, importantly. And so the space of orbit is a smooth manifold, none other than the base of the principal bundle. So why do we need it? Well, we want to model those locally smooth profiles in the group. They will act on something that will come later, but first we want to lay our hands on locally smooth profiles in the group. How do we model them? As we anticipated, sections of a certain bundle. Okay? Well, you note that we started with automorphisms of the principal bundle P, while sort of covering the identity diffeomorphism on the base, so the slice textbook. But anyway, so with a little work, you can show that these are in a bijection, and actually it's a group isomorphism with global sections of the so-called adjoint bundle. The adjoint bundle being the quotient manifold for the following manifold and G action on it. So you extend P by G. On it, you have the diagonal action defining here lambda, adjoint here. You divide out the action. The defining action on P being free and proper. This property is inherited by this extended bundle over X, and so we have a smooth manifold structure on the quotient, and this is called the adjoint bundle. And I will show to you that sections of the adjoint bundle can be locally represented as smooth profiles over space-time in the group G. So they do model what we want them to model, namely those point-dependent, in space-time, symmetry transformations. But before we get there, we need to define what the fields are. And we'll play on the same quotient manifold theorem. And for that, in order to understand the whole construction, we need a little piece of sort of higher geometry in the sense of more involved geometry. So start with an action. Okay, first just I will give you the background, the more refined background, but for the moment just replay the quotient manifold theorem. So let's assume we have an action, as we did, because these were global symmetries, of our Lie group on F, this being the space of internal degrees of freedom of a field theory. Okay? We can extend P by F, since the action of G on P has those nice properties, which are then inherited by P times F, we can quotient out this action. This action is free and proper. We can quotient it out, apply the quotient manifold theorem, and we get the so-called associated bundle, which is just this quotient manifold. All right? And it's a bundle over the same manifold as the base of the original principal bundle. And furthermore, and importantly, this bundle has the typical fiber F. So here we are. Fingers crossed. We have a bundle whose typical fiber is the same F, so the same internal degrees of freedom. By the same token, we also have this bundle at P, whose typical fiber is G. So we have a bundle of groups and a bundle of internal degrees of freedom, and now we just have to make the two come together. When I was young, there was this song, "Come Together." So sorry, it's when you, as you age, those songs replay in your head on such unexpected. Come together one more time. Yeah, there were different comings together. Many people came. And came together, but right, never mind. It's not a lecture on that. Anyway, so let's make the hadron bundle act on the associated bundle. It's very simple. It's a fiber-wise action. Very good, all the better, because it means that there will be a point-dependent group action on sections of our candidate matter bundle. And indeed, so first of all, this descends to an action of the space of this group of gauge transformations, this group of global sections of the hadron bundle, which, as you recall, were in a structural bijection with automorphisms of the principal bundle, so gauge transformations, on global sections of the associated bundles to be interpreted as matter fields, charged matter fields. All right, and now, in order to see that we have really realized our goal, let's go to local description using the fact that there are further bijections and structural bijections. So for a generic associated bundle, you find out that global sections of the associated bundle are in a one-to-one correspondence with G equivariant maps from P, the total space of the principal bundle, the gauge bundle, into the typical fiber of this. Okay? And by the same token, but also more structurally, there is an isomorphism of groups of global sections of the hadron bundle and G equivariant maps from P to G. Now here, the action of G on P is the defining one, R, and the action on F is lambda. And here, the action on P is again R, the defining one, and the one on G is the hadron touch. All right, good. What does it mean? It means that you see, since you have a map from P to F, you can interpret a matter field as a map from P to F with extra properties. It means that if you now have a section into P, which, given non-trivial topology of your laboratory geometry, may only exist locally, you can pull back this map by a local section and obtain a local gauge. You can choose a gauge for your matter field and a gauge for your gauge transformation. Gauge meaning a local description, given by a choice of a local trivialization of this master principal bundle. Because now if you pull back such an object, of which you are now entitled to think as a matter field, you get a locally smooth map from an open set on which the section sigma exists into F. Cool, that's what we wanted. We wanted to have this physical picture in which we have smooth maps into the space of internal degrees of freedom. And a gauge transformation is none other than a smooth map from O to G, so a smooth profile in the group. And the two can act on one another in a simple fashion, modeled on number. So we have realized our goal. Mind you, if you have a non-trivial topology, there is no global section of the principal bundle. What am I saying? I'm saying that there are bundles which do not admit global sections. Because as it happens with principal bundles, it's a rule that a global section is the same as a global trivialization. There's a one-to-one correspondence between sections and trivializations. So in the Aharonov bomb context, you're not allowed to think that, let's take a trivial bundle, that it will be fine. you may not be able to do so, depending on F, on the class F. Okay, so now let me think about it. Maybe I will skip I will sort of skip the abstract, well, maybe, no, absolutely. Let me skip the abstract part of my talk where I kind of where I'm telling you about the universal construction behind the gauging. I will come back to that when we need it, and we will need it when we discuss this third geometrization, that is integration over isoclasses of principal bundles when reducing the space of internal degrees of freedom, and why we should really take all of them into account. That will invoke then will invoke the Yoneda lemma basically, and see that we have to make this integration over isoclasses. So let me just jump this and instead jump right on the subject that has brought us here, namely, how do we now that we have constructed the matter bundle on which the gauge group acts, how do we arrive at a coupling between gauge fields, the messenger fields, which live there on the principal bundle, P, mind you, the principal connection, to the charged matter field? And here's how it works. So let me simplify matters here. And instead of considering a generic Lagrangian density for the matter fields, let me consider one in I have tensorial couplings. So I've already given you an example of a field theory, 0 plus 1 dimensional field theory, in which there are non-tensorial couplings, namely the coupling of an external electromagnetic field to the embedding field X was given by a holonomy. So not guys like that. We just want to have a Lagrangian density defined in terms of tensors on F, on the space of internal degrees of freedom. As for example, the Klein-Gordon coupling, which is just the coupling of a metric on the space of internal degrees of freedom to the two derivatives of fields. Right? This is the standard Klein-Gordon coupling. And let me just consider such tensorial couplings, which are just mappings from some tensor power of the tangent of the space of internal degrees of freedom into functions on that space of internal degrees of freedom. I will further assume that the bundle is trivial. See, right? And now in order to have a symmetry of a field theory defined in terms of those tensors, the simplest thing we can think of is to assume that all these tensors are actually G-invariant. So there's a tangent lift of the action of the group on F, TF, all right? And there we assume the tensors to be G-invariant. What then? Well, you would be naively led to the following rest. Now that we have realized that having replaced the original field bundle by the associated bundle with the same typical bundle, and having modeled our local symmetry on sections on the associated bundle, which acts on those sections of the, an adjoint bundle, which act on the sections of the associated bundle. Having realized those global sections of the associated bundles locally as mappings into F, we could just take derivatives of these and plug them into the original tensor, feed them into the original tensor. So here, what you have is functions into F, and now I could just plug in derivatives of functions, and now I'll just plug in derivatives of those locally smooth functions. So what is wrong with this naive thinking? The wrong is that, of course, I mean, you can write it like that, but what about if you change the gauge, the local gauge, sigma, which enabled you to represent this global section of the associated bundle as something as tangible as the smooth map from the support of this section into F? Well, there is actually, technically speaking, there is a gauge transformation. As you change the section, there is a gauge transformation. And just try to differentiate this object, right? There was this formula, I'm sorry. Try to differentiate this object. Now, this depends on the point in space-time, and this depends on the point of space. Previously, you have global symmetries, so the group element here, the profile in the group was flat, was constant. So as you differentiate, you wouldn't see it. You'd just get a tensorial transformation law for the standard derivative, right? Tensorial. But now this guy depends on a point in space-time, so you get a correction proportional to the derivative of the gauge transformation. Bad luck, right? So you have to correct the coupling of the field F. I mean, this tensorial coupling. You have to replace the standard derivation by something. But luckily, the connection one form, the principal connection one form, also has a non-tensorial, or should I say, tensorial affine transformation law under gauge transformations. And this is the law. I mean, sort of, never mind that I cannot write. Never mind the precise form, but the logic, the structure is important. There is the tensorial part. There should be an A here. There is a tensorial transformation of the gauge field, plus there is an inhomogeneous bit, which is just the derivative of the gauge transformation. And as it happens, if you look at this formula more closely, if you contract it with the fundamental vector field, the non-tensorial bit in the transformation law for the principal connection one form cancels out the correction to the tensorial transformation of the standard derivative. So if you put the two together, the whole thing will transform as a tensor in the tangent, sitting in the tangent, so you can again contract it with an invariant tensor to form what is now, with the gauge field coupled to the matter field, what is now a gauge invariant. Well, local description of the gauge invariant field theory. So now we have arrived at the notion of the covariant derivative. You may have seen it at work for the associated bundle given by a vector bundle, and then this really simplifies matter because this depends linearly on the field acted upon, this phi. And then you see, so now the question is, how should I glue the local description? Now I know what to do locally over my spacetime. I should take the same tensors, the invariant ones, plug in, where I previously plugged in derivatives of fields which are smooth functions into F, the space of internal degrees of freedom. I should plug in covariant derivatives of representations of the corresponding global sections of the associated bundles in local gauges. And now so the question is, how do I glue these local descriptions? Well, I should choose domains in space-time over which the gauges, the local gauges exist, so the sigmas, and then draw a boundary between those domains anywhere in the double overlap of the supports of the respective sections. Draw a border there, and up to the border from one side, use one local description, and on the other side of the border, use the other gauge, local gauge, and write down the local action functional or local Lagrangian density there. But how do we choose the border? Doesn't matter. As long as we move in the intersection of the two domains of the two local gauges, if we change the location of the border, the action functional changes by a gauge transformation given by the transition functions, translating that from one section to the other. And you know that the formula is gauge invariant, so it won't matter where, choice, where we draw the border. Good. Excellent. So now we have a formula for the action functional written in terms of those same smooth, but now locally so, smooth maps into the former space of internal degrees of freedom, which, however, being minimally coupled, as people say, is now invariant under the gauge group, which is the group of locally represented by smooth profiles in the group. And now you must have seen things like objects like that. So this is part of the standard model, and the standard model of fundamental interactions. So inscriptions like that in this huge 1 or 4 pages long model of fundamental interactions, where here I have the Higgs field. It's a complex Higgs field, and these are messenger fields before the Higgsing, which gives some of them mass. So these fields are linear combinations of the W plus, W minus, Z and the hypercharged field, of which some combination survives as the massless photon, and the rest gets a mass. But still, geometrically, it's the same object, right? So these things actually exist in nature. I'm not blowing smoke here. Why try to bit high? So what's the overarching geometry? So we see, I had this one form which was taking me from TP to the Lie algebra. So let's take now this one form together with the projection in P and get from TP to P times the Lie algebra. This is actually the vertical distribution in P, the kernel of the tangent of the projection, spanned on the fundamental vector fields for the action, for the right action, finding action of G. And now you see, since this is actually a surjective submersion, so it's a maximal and hence constant rank vector bundle vector bundle morphism. By the constant rank theorem for vector bundles, you see that its kernel is a subbundle in TP. And what is the subbundle? It hooks up with Kashka's talk. But here it's not a contact structure, it's really a proper subbundle. Namely, it's a horizontal subbundle. So choosing this one form, to which we were led by cohomological considerations, we're actually choosing witness some complement in the tangent to the always existing vertical distribution, because the vertical distribution is just given by the kernel of the tangent of another surjective submersion. All right? Hence a subbundle. And it's, since A being G equivariant, now this horizontal distribution is G invariant. Okay? And what does this give us? It gives us a very nice, neat description of the covariant derivative. Because, now look, I mean, never mind the formulae, but what you can do is the following. Start with P times F, as we started in this, before gauge fields enter the game. You have P times F. Choose a horizontal distribution on P times F, given by the horizontal distribution on P. Okay? It's supposed to be that repointing in isomorphic to the tangent of the base. Okay? And now note that this distribution is G invariant, which means that as you project out the diagonal action of G on P times F, it survives, it descends. So it gives us a horizontal distribution on the quotient manifold, and so on the associated bundle, on the bundle of fields in our gauge field theory. And then, as Kashka explained to us, you can think about such sub-bundles as kernels of, in our case, globally smooth one form. Okay, and actually this one form here, in question here, can be fully expressed in terms of the local gauge potentials for our principal bundle, and the fundamental vector fields. Never mind the concrete expression, but it can be written out concretely. And so we have a connection one form on the associated bundle. And now a beautiful formula. It's beautiful. It's beautiful. It's really beautiful. But anyway, and now what's fucking beautiful. So anyway, as we're getting back. But anyway, so now you get a nice formula for the covariant derivative, which is just a projection of the standard differentiation with the help of this projector that I introduced, in the way that the kernel is the induced horizontal distribution. And now you see that it's automatically, although in a subtle way, gauge invariant. Namely, if you simultaneously gauge rotate the gauge field on which it depends and pull back by the gauge transformation, the form doesn't change. And this can be used to say that the thus defined covariant derivative is not a red herring, which means it's not just a derivative, but it's also covariant. Okay? Excellent. But now, the sad news is that great news is that we have those non-tensorial field theories, but the sad news is that they don't follow the same pattern. We cannot just minimally couple and go fishing, or whatever. Because for example, for those field theories defined in terms of holonomies, this minimal coupling recipe doesn't work. So I know that you were taught that at high school that minimal coupling is the end of the world. It is not. Oh, I'm sorry to shatter your world. If I do. Hopefully I don't, but anyway. So let's consider the toy model. But now be careful, because there will be two principal bundles. The U1 bundle, I will refer to it by the term electromagnetic bundle, which I introduced previously to geometrize the Maxwell field. I haven't gauged anything there. It was a background. And there will be another bundle which will be used to gauge a symmetry, which will be some isometry on X in which the point-like particle propagates. Okay? But let's start with what we had before. So this non-tensorial action functional, or rather Dirac-Feynman amplitude, so the exponentiated term that gives us geodesic motion, and the holonomy, which gives us Lorentz deflection from geodesic propagation. First, we have to identify the structure, well, let's start with the infinitesimal one, of global symmetries of this action functional. So how we go about that? Well, we will be modeling symmetries, global symmetries, by flows of vector fields in X, which is where the particle propagates. From the point of view of this field theory that I mentioned earlier, the field theory is the 0 plus 1 dimensional field theory with the space of internal degrees of freedom given by X. Just to put the whole thing under one big label of field theories. And now we have diffeomorphisms given by flows of vector fields on the space of internal degrees of freedom, as before. So on X, and look for those which preserve the Dirac-Feynman amplitude. What do I mean by that? I post-compose the mapping from S1 into X with the flow. So I flow the loop in X, which is the field configuration in X. I flow it along the vector field and request that the action functional doesn't change along the flow. What do I find? Again, a nice exercise. If I assume that the flow is isometric, so it preserves the metric, then I find out this funny expression. The contraction of the vector of the velocity vector field, if you will, along the flow, with F. F is the Maxwell field, should be exact. It should be closed naturally because F should be an invariant tensor under our symmetries, but more than that, it should be exact. And so it defines a global zero form function, which people sometimes call co-momentum. It's associated to any vector field of small symmetries of my action functional. I now associate a zero form on that space, on X. So altogether, they combine into a section of what may look to you somewhat pretentious, but the point is that when you start considering loops in X and membranes in X, this whole thing generalizes. So it's better to describe it in this unified picture from the start, from the beginning. So this pair, a vector field and a function, can be viewed as a section in this Hitchin-like generalized tangent bundle over X, where I have the standard tangent bundle, and here, as it happens, the zero exterior power of the cotangent, so X times R. I'm just saying that for loops it would be the cotangent bundle. For membranes, two-dimensional ones, it would be the second exterior power of the cotangent bundle, and so on and so forth. So the section here is a vector field, the section there is a function. Okay. And so what? Well, there is an algebraic structure on the set of sections of this bundle, which is here it happens to be a Lie algebroid structure, but more generally it would be a Courant algebroid or a more generic Vinogradov algebroid. I won't go there, at least not at the moment. Here, accidentally, it is the Lie algebroid. So Twisted a la those who know or would like to read up more on the subject, a la Schwerer and Weinstein by this two form. And what is the Lie algebroid? I will tell you in a moment. For the moment, we just have a bracket structure of a section, okay? Which lifts, mind you, it lifts the commutative bracket on the tangent subpart, okay? And as it happens, if you look at those symmetry sections, so a vector field and the function, this sort of quasi-Hamiltonian for V, it's contracted with that, then you find out that the bracket closes on this subset. So if I take two symmetric sections, the bracket is again a symmetric section. Aha. So under some circumstances, this would be a Lie subalgebroid. And this is indeed what measures, what quantifies the so-called small gauge anomaly. Okay, so first let me tell you what a Lie algebroid is. I'll come back to that later on, but for the moment, just let me tell you what it is. So briefly, so it's a vector bundle over some base, equipped with a vector bundle morphism into another vector bundle canonically associated with that base, namely its tangent bundle. So to any section of that bundle, I associate a vector field over its base, and in such a way that I can phrase this so-called Leibniz property for the Lie bracket that exists on sections of this bundle. So there's the Lie bracket, there's the Jacobi identity. I have to stress, there is no Jacobi identity, there is Jacobi identity, at least in my corner of the world. Don't make this mistake. But then you see sections of a vector bundle over a given base form a module under smooth functions on the base by just pointwise multiplication. So it is natural to ask how the two structures talk together. We have this bracket, and brackets in the Lie algebraic context are always like differential derivations of the algebra. Well, we don't have an algebra structure on E, but a Lie algebra structure on the sections. And now, what about multiplying a section by smooth functions on the smooth function on the base? Well, it should satisfy this Leibniz property. So it's really like the derivation. Just we derive the function relative to with respect to the vector field associated with one of the sections here. Okay, good. But now back to physics, because that's what we would like to discuss. So now you may proceed in the following way. We have this holonomy for the magnetic bundle, and we'd like to correct it. We know how to correct the metric. We just do the minimal coupling, replace the derivatives by covariant derivatives of the local gauges of the global sections of the associated bundle. But how do we deal with I have time until tomorrow. Yeah, good. Raise yourselves. So anyway, how do we correct the holonomy thing? The holonomy term in the action function. Well, so remember what happened if we had an invariant tensor. There was something like there was this covariant derivative coupled replacing. Okay, I should maybe write it. So there was this global gauge field which was like pulled back by x up, which means there was A coupled to Tx. And so the first thing I would come up with is A dx, right? X squared. But this means that I'm replacing the original holonomy with something which depends linearly on the gauge field in the gauging bundle P. So let's try this. And this is called minimal coupling, but we'll find conditions. So let's replace the holonomy by something from the functional on X envelope polynomial in the local gauges of the gauge field A. So like we take the holonomy as it stands and add to it the exponential of a functional combination of powers of the gauge field. That comes from minimal coupling, naturally. But then it turns so, as it happens, if you request that the resulting corrected holonomy be invariant under small gauge transformation, Polish transformation. These are profiles in the group arbitrarily close to the identity profile. To the flat profile giving taking value E, the neutral element in the group everywhere. Okay? And so these are these are vector fields, if you will, on the associated bundle. So if you request this infinitesimal gauge invariance, you find out that you cannot add any correction to the holonomy, but something which depends linearly on A, not surprising, but with a very particular functional coefficient, namely the comomentum. And never mind how it captures. The comomentum is a mapping from the Lie algebra to functions on X. So if I post-compose A, which takes values in the Lie algebra, with comomentum, it knows how to eat the vector in the Lie algebra and spit out a function. So this is a function which I can integrate. Okay? All right, good. But then not any. So the kappa has to be there. And kappa has to be constrained if I request infinitesimal gauge invariance of the thus corrected holonomy of the electromagnetic bundle along my Aharonov loop. Namely, this comomentum has to satisfy this condition. So at first you think, what the hell? But then you realize that kappa is a structural map which maps from the Lie algebra, where there is an action of G, to functions on X, where there is an action of G by Kullback. And so this is a notion of this is the condition of equivariance of kappa. Right? But I told you about how symmetric sections are special sections in this generalized tangent bundle. So does this equation have an interpretation in terms of this closed subset of sections closed under the bracket, under the Lie bracket, this fancy Scheverer-Weinstein twisted Lie bracket on the space of sections of the generalized tangent bundle? Does it know about this condition? Can it be interpreted? And yes, it can. And it propagates to charged loops, charged membranes, and so on and so forth. Namely, it has the interpretation of the functional span of the symmetric sections becoming, with the bracket restricted to them, a Lie algebroid. The Jacobi identity has to vanish. It has to be an involutive distribution. And then it's not any Lie algebroid, but it's the tangent Lie algebroid of the action groupoid, of which I will tell you more in the second or the third lecture. Categorification of symmetries. As we turn on the Maxwell field, the symmetries of this new guy, of the charged particle, are not just diffeomorphisms, like Lie algebra, running infinitesimally, but they are something that integrates the tangent Lie algebra, if they're gaugeable. And that's a Lie groupoid. And that's already a category, the first notion of higher notion of symmetry. Okay. So now you see what we should do is, as the whole procedure suggests to us, we should take the original Maxwell bundle and correct it by the trivial U1 bundle with the connection fixed by these considerations, So think of the corrected expression as a holonomy for the tensor product of two bundles, the original Maxwell bundle and a trivial bundle, because here there's like a global connection one form, a trivial U1 bundle with connection given by this formula, but this formula lives on P times, well, O in this case, O times X. So we have to extend so we have to put the new bundle on, in general, P times X, naturally. So on P, there will live our, here I should remove sigma pullback. Here there will live A. Omega is given in terms of kappa, which lives on X. So this trivial correction, however trivial, it sits astride between P and X. And it is here that we put the corrected bundle. And its holonomy has a chance of giving us the correct minimal coupling extension of the original holonomy prescription for the topological term in the action functional for the point-like charge in an external Maxwell field with the symmetry G gauge. Okay? But when will it happen? The answer is here. See, I have put something on P times X. How far are we from the space of fields of the gauge field theory? A quotienting away. Because if we now mod out by G, we will get our associated bundle whose sections can that is fields, can be used to pull back the object, unless it doesn't descend to the quotient. So now the question can be phrased like so. Under what circumstances does a bundle, a U1 bundle, on a given space, equipped with the action of a group, descend to the smooth quotient, granted that, as in this case, the quotient exists? And I could give you a sort of a nice formula saying that the category of bundles, C or CX bundles, or U1 bundles with connection on the base of a principal bundle is in functorial equivalent with the category of bundles on the total space of the principal bundle, but with extra structure, which is called the equivariant structure, G equivariant structure. But that's a mouthful, right? So we'll derive it. Except that we won't. So I have whetted your appetite, I suppose, with the question, but now we'll circumnavigate the formal obstacle, meaning you have to read books. I mean, it's good to read books, but there are so many books, so I'll make you, I'll make you skip one of those, or some sort of entice you to read it by deriving the equivariant structure on the Maxwell bundle as a condition for gauging the symmetry G, and that will go via defects, which will be another fine thing about the gauge field theory. So it will be a field theory with defects. We will leave the smooth field theory paradigm and we'll deal with field theories in which field configurations are locally smooth and the jumps are, in this case, controlled by field. We can also leave this paradigm too. We can leave all paradigms and be happy with it. But anyway, we will not move far from this paradigm in that the discontinuities of fields will be given by the action of the group. How so? Let me just flash it at you. So I told you that if I have a global section of the associated bundle, which is the field in the field theory with the symmetry gauge, it can be made sense of locally as a locally smooth map into F. But then those local models of the field are discontinuous, because as we pass from the domain of one section to another, to the domain of the other section of P, there is a jump. Jump by what? By the division map evaluated on the two sections, the division map of the principal bundle, meaning by the transition mapping for the bundle. And where does the transition mapping take values? In the group. So, in other words, we'll have defects. So, alternatively, we can think of this gauge theory as a gauge theory as before, fields taking values in F, in the original space of internal degrees of freedom, but now jumping and arbitrary points, right? By the action of the group mediated by the transition mappings of the gauge bundle P. And this is what I want to talk about in the next lecture: how to make sense of such a field theory with defect in the presence of higher geometry on the space of internal degrees of freedom F already, like this Maxwell bundle. I will keep it very simple as hitherto, because it makes no point to go directly to jerks, which is another goal in my talk, and to show you equivariant structure there, because there you might think that, you really need to do jerks to see the equivariant structure. Let's not. Right? No, you can see it in this point particle picture, this equivariant structure. Okay, as you make sense of this defect infested, or as I prefer to think, embellished field theory. Okay, so thank you for your attention.